All right, let's look at 4.5. So for number 5, we have y is equal to f of x is equal to x minus 4 cubed. That means the domain of this thing, when I look at that, it's going to be all reals because this is a polynomial when you multiply it out. The x-intercept is where y equals 0. So 0 is equal to x minus 4 cubed. That means that x is equal to 0 or x is equal to 4. So that means that 0, 0, and 4, 0 are our two x-intercepts. Know that our y-intercepts are where x is equal to 0. And so if you put in 0, you get out 0. So that means 0, 0. So far, we know that our domain is all reals. Our x and our y-intercepts are listed here. Okay? X-intercepts, y-intercepts. If I want to know increasing, decreasing, then what I'm going to do is step 1 is critical values. Critical values, which is where the derivative equals 0. So when I take that first derivative, it's going to be what? First derivative of second. First derivative of second plus the second times the derivative of the first, right? But now when I look at this, I need to see two big terms, this one and this one. When I look what's common to both terms, it looks like there are two of these x minus 4s that live in both. So if I pull out x minus 4 squared, then who would be left behind? Well, it would be 3x plus x minus 4. So when we simplify, it's this, and it's what? 4x minus 4. So where is the where is the derivative equal to 0 or the derivative undefined? It's undefined nowhere, because if you multiply that out, it is a polynomial. But then where is this squared 4x minus 4 equal to 0? Well, either this is 0 or this is 0. And that's telling you that 4 and 1 are your two critical values, right? So if these are my critical values, those are my critical values, I'm going to use those to partition my number line. So step 2, so that's step 1. Step 2 is to partition. And by partitioning, I mean I'm going to take 1 and 4 and break up the number line into 3 pieces, excuse me. So step thrice is going to be to chart. So my first interval is negative infinity to 1, then 1 to 4, and 4 to infinity. So then I take the pieces of my derivative, which are x minus 4 that got squared, and 4x minus 4. That's going to tell me about my derivative, which will tell me about f. Well, great. This is always positive. For something like 2 inside this interval, this is going to be positive. For something like negative really, really big, this is going to be negative. For something like positive really, really big, that's going to be positive. So I think for f, we know the following, that this is going to be decreasing, increasing, increasing, which makes sense. And we also know that f prime changes sign from negative to positive at x equals -1, which implies a local minimum. So that would be enough to tell me about my intervals of increase, decrease, and my local minimum. That would be enough to write, to show me. So that's increase, decrease, local mins and maxes. But then when we have our concavity conversation, so this is 5 continued. If I talk about concavity, then step 1 is the second derivative equal to 0, or is to find the critical values, which is where second derivative equals 0, or the second derivative is undefined. Well, guess what that means? That means I take my second derivative. So my first derivative looked like this. So I'm going to copy it. So if my first derivative is this, then my second derivative is just going to be the derivative of this thing. So it's going to be first derivative of second plus the second times the derivative of the first. Right? Okay. So let's see. First or second derivative first. Then I guess I say, okay, so what's common to this? I now view it as two terms because they're separated by plus or minus. And I see that I've got an x minus 4 in here and here. So I'm going to pull that out to the front, and I'm going to have an x minus 4. Well, who would be left behind? An x minus 4. Let's see, 1x minus 4. I think I can also pull out a 4. Because before I do any work, let me rewrite this as x minus 4 to the fourth with a 4. This is going to be 4 times x minus 1, 2x minus 4. I'm just going to pull out a 4 out of those. So that means not only can I pull out an x minus 4, I think I can also pull out a 4 out of both terms. So I'm going to pull that 4 up here and pull out this x minus 4. So who would be left? Well, who would be left behind? I guess that shouldn't be a to the fourth. Sorry, this is a squared. It's just a squared. So when you pull out 1, 1's left behind. When you pull out 1, none are left behind. So this is going to be plus, and I guess it's just going to be an x minus 1 times a 2, right? 2 times an x minus 1 and x minus 4, and yep, I'm right. And so it's 4 times x minus 4, and then this in here, do you agree that this is just simply 2x minus 2, this is x minus 4, it's all that added together is going to be a 3x minus 6. And so if I pull out that 3 out of, there's a 3 that's common to this term and this term. So I pull that out, I really have 12 x minus 4, x minus 2. Make sure that's readable. X minus 4, x minus 2 is what my second derivative happens to be. So if you ask me where that's equal to 0 or where that's undefined, I say it's undefined nowhere because it's a polynomial if you multiply it all out. Here I get this x minus 4, x minus 2. Well, either 12 equals 0, which never happens. This equals 0, which gives me 4. Or this equals 0, which gives me 2. These are my possible critical values. So then step 2 is to partition. So I get 2 and 4. And then step 3 is to chart. So if I chart that sucker, maybe I'll do it right here. I'm going to have negative infinity to 2, 2 to 4, and 4 to infinity. So when I do that, what are my pieces going to be up here? Well, I'm going to have a 12, which is always positive, right? I have an x minus 4 and an x minus 2. That's going to tell me about my second derivative, which will tell me about f. Notice all of those just came as factors from the second derivative. So great thing, this is always positive. For really big x values, this and this are also positive. So that would give me concave up. Give me concave up. For something like 3, this is going to be positive, but this is negative. So I'm going to get negative, which is concave down. For something really negative, that and that are going to be negative, which will give me a positive, which gives me concave up. So let me see. This thing goes concave up, concave down, concave up. Yes, that's correct. And so what we see is that f double prime changes sign at x is equal to 2, x is equal to 4, which implies f has an inflection point at both of those different values. So now we're ready to put it all together. So when we think about what this looks like, first we have our x and y intercepts. It seems like, when we go back and look, it seems like x equals 0 and x equals 4 were our only intercepts. So we got 0 and 4, right? And then we said that our function was decreasing all the way down. So it's got to go through this, and then it's decreasing. And we had a local minimum at 1. But then we know in the next interval it's increasing, right? Let me do this, right? So then we know it's increasing, and then it has an inflection point. It has an inflection point at 2, where it goes from concave up to concave down. So it does something like this, yes? And then it goes from concave down to concave up at 4. So our graph is going to look something like this. So it's decreasing, and then it's increasing, and then increasing. But then again, if we look at the second derivative, we have to go concave up, concave up, concave down, concave up. And we now have our graph of f of x. Again, just a sketch of x minus 4 cubed. All right, so that's 5. And then we look at, I think the next one was 9, correct? 9 and then 12. So if I look at 9, so now how is 9 different? Well, when you look at 9, this is f of x is equal to x over x minus 1. So first, when I look at the domain of this thing, we see x can't be 1 because that would make the denominator 0. So my domain is negative infinity to 1, and then 1 to infinity. Because remember, we worry about square root of a negative and stuff over 0. So stuff over 0 is only going to happen where the denominator is equal to 0. So that means this, which means x can't be 1. And that's why we get this domain. Okay. That's the domain. The x-intercepts are where y equals 0. So I set the whole fraction equal to 0. That means x must have been 0. So 0, 0 is one of our asymptotes. The y-intercept is where x equals 0. So if I plug in 0 into this thing, I get 0 over negative 1, which is 0. So that means, again, 0, 0, I didn't have to do it, is a point on our graph. So if I take 9 and continue, I need to now do increasing. Oh, crap. On that last one, I guess I didn't do my asymptotes. But I think you would have seen, just to go back and talk about asymptotes on that, let's just remind ourselves. I'll put a little note here. Sorry about that. So note, vertical asymptotes. Vertical asymptotes are where the denominator equals 0, yes. That happens nowhere. And then horizontal asymptotes, you want to look at the limit as x goes to infinity of f of x, which is infinity, or you can take the limit as x goes to negative infinity. And for both of those, it's going to be infinity, so we have no horizontal asymptotes for this thing, right? Cool. That was for the last one. So for this one, I think after x and y intercepts, we should worry about those asymptotes. So before we do increasing, decreasing, let's do our vertical asymptotes. So vertical asymptotes are where the denominator equals 0. So that means we're going to have 1 at 1. And a horizontal asymptote is what happens in the long run. And so for us, it's this over this. Well, notice that has the form of infinity over infinity, so we can use L'Hopital's rule. And so we end up getting the limit as x goes to infinity of 1 over 1, which equals 1. So y equals 1 is a horizontal asymptote. So we have a vertical asymptote at 1. Turns out that we have a horizontal asymptote at y equals 1. All right, now we're ready to talk about increasing, decreasing. And so step 1 is critical values where the derivative equals 0 or the derivative is undefined. Let's see. So the derivative of the sucker. So for number 9, if I look at the derivative of the sucker, I'm going to do low d high. So I'm going to take low derivative of high, which is 1, minus high derivative of low, which is 1, all over low squared. So you're just going to end up getting negative 1 over x minus 1 squared. So I want to know where's the derivative equal to 0. Well, that's only where the numerator equals 0, but that happens nowhere. And then I ask where is f prime undefined? And for us, that's where the denominator equals 0. And so I end up getting x equals 1, right? And we know that this is a vertical asymptote, right? Recall that that's a vertical asymptote. So it's still going to be used to partition our number line, but we just got to remember it can't be a min or a max. All right, so this thing is not going to have a local min or a max at all, anywhere. It's just going to have a vertical asymptote. So this is number 9. We're doing increasing, decreasing. We need to do step number dose. So step 2 is to partition. And so we take the number line and we cut it with 1. And so step 3, we're going to chart. We have negative infinity to 1, 1 to infinity. We're going to do our chart, but this time what our factor is going to be. It's going to be negative 1. It's going to be negative 1 and x minus 1 squared. And we could have seen earlier that this is always negative and this is always positive. It turns out that the derivative is always negative, which means this function is always decreasing, which is pretty interesting. Also, don't forget when you chart, I would make this a dotted line to really remind you that you've got a vertical asymptote at x is equal to 1, right? So you don't get confused and think that it could have been a min or max. All right, so we have no mins or maxes since f prime never changes sign. F prime never changes sign. So now we're ready to do concavity. So this is enough to tell me that this is where f is decreasing and this is where f is decreasing. So concavity, step number 1 is critical values, which are where the second derivative equals 0 or second derivative undefined. Hopefully I'll get this done before people come in. Oh, this takes a while. Let's see, second derivative. So if my first derivative was negative 1, so negative 1 over x minus 1 squared, that means my second derivative is just the derivative of this thing. So before I do anything, watch what I'm going to do. I'm going to rewrite it as negative x minus 1 to the negative second, and then I'm going to take its derivative. That's just going to make it easier. So its derivative is going to be 2x minus 1 to the negative third times a 1. So it's going to be 2 over x minus 1 cubed. What's up? And so that's this. And so what does that mean? That's nice that you got a helper. So the second derivative equals 0. is where 2 equals 0. So that's nowhere. And then second derivative undefined is going to be where the denominator equals 0. So it's going to be this, which means x is equal to 1. But we already know at x equals 1, we have a vertical asymptote. Vertical asymptote. So this thing has no inflection points. No inflection points. So we're now ready to graph this thing. Actually, no. Oh, sorry. I need to do step 2, which is partition. Boom, boom, 1. We'll show it's a vertical asymptote. And so step 3, let me move this over. Step 3. So step 3 is to chart. And so for charting on this one, I'm going to go negative what? Infinity to 1, 1 to infinity. And so what are my pieces going to be? It's going to be 3x minus 1 cubed. It's going to tell me about this and this. So this is always positive. For big X, it's positive. For big negative X, it's negative. So second derivative is negative. That means concave down. Second derivative is positive. That's concave up. Even though that changes sign, remember there are no inflection points because vertical asymptote means it can't be an inflection point because there's no point on the graph. So now we put it all together. And when we put it all together and try and draw this sucker, it says that all the way back, so our x-intercepts and y-intercepts, we just had 0, 0, right? 0, 0, a vertical asymptote at x is equal to 1. And we said that our function was decreasing everywhere. So just when I start to draw it, I know it's going to decrease and then maybe go down like that. I know it's going to decrease over here, but notice, ooh, that's interesting. Do I have a horizontal asymptote? So this thing has a horizontal asymptote at 1. Okay, so this thing has a horizontal asymptote at y equals 1, right? So my guess is it would do something like this. Then over here, again, we want it to decrease and get closer and closer to y equals 1. Notice it can't start here and decrease forever because then it would have to decrease over here and it would cross. So I think it's going to look something like this. So now it's decreasing forever. The other thing we check is we want to check concavity. So notice concavity needs to be concave down and then concave up. And from my picture, I have concave down and then concave up. So that's what my picture is going to look like. My vertical asymptote. I'll do the rest of them soon. Peace out.